We're going to look at light as an example of a wave undergoing reflection. So remember that light is a type of electromagnetic radiation or electromagnetic wave. When it reflects, it is behaving like a wave. Electromagnetic radiation is created by oscillating electric and magnetic fields. So let's take a look at what that would look like. And you can see here for the red, you've got the magnetic field, which is oscillating on the horizontal plane. And then you have the blue wave, which is the electric field, and that is oscillating on the vertical plane. And those are perpendicular to each other. So this is what electromagnetic radiation would look like as a wave. So these are the fields that are oscillating. Remember that in a vacuum, all light travels at 3 times 10 to the 8th meters per second, but also remember that waves can travel at different speeds when moving through different media. So the speed of light changes if it's moving through glass or air or water. When we do diagrams for light, we typically represent just a ray, but remember that a ray is an indication of the direction that a wave is traveling, and rays are always drawn perpendicular to wave fronts. So here we're going to look at a ray diagram for reflection. So here we're looking at a perfectly flat, smooth surface, and we're looking at a ray, right, which represents a wave of light incoming on the surface. So it hits the surface. So we call this the incident ray, right? It's the thing that's happening. A ray is hitting the surface. And whenever we deal with rays, we always draw a line that is perpendicular to the surface at the point where the light hits the surface. And we call that the normal. So normal in math meaning perpendicular. So it is perpendicular to the surface. So whenever we deal with rays, we always want to measure the angle between the ray and the normal, okay? Not the surface, between the ray and the normal, and that's why we have to draw the normal first, right? And this is called the angle of incidence. We call it theta 1. Theta is just a variable like x that is traditionally used for angles. And the law of reflection is pretty simple. Right? The angle that it comes in at is the same angle that it goes out at. So we call the ray that reflects off the surface, we call that the reflected ray. And we call the angle between the reflected ray and the normal the angle of reflection. Okay, you already know this law. The law of reflection states that the angle of incidence equals the angle of reflection. Seems very straightforward. And if we look at a situation where the surface, oh, sorry, just a reminder, again, angles are always measured between the ray and the normal. Very important. Clearly, I thought it was very important. So what we're going to look at here is reflection off of a smooth surface. So what we're showing is we're showing several rays, right? So basically we're showing a wave or light that's coming in, all heading in the same direction. And you can see that if we drew a normal to the surface at every single one of those incident points, right, and then we drew every single angle of incidence, we would say they would all be the same, right, because the rays are parallel to each other and we have a flat surface. And you can see as we draw each angle of reflection and then the reflected ray, voila, you can see that all of the reflected light comes out also traveling parallel in the same direction. This is called regular reflection. This is off of a smooth surface. Now, when we say smooth, right, it's kind of a relative term. So I want you to just imagine the table in front of you. Okay, so the table seems smooth. So why don't we see our reflection in a table? So if we kind of imagine a microscopic view, right, or a zoomed in view of the surface of the table, it might potentially look like this. Let's take the same set of rays. So this is light coming in, right? But now you'll notice that in every point where the light hits, the surface is not at the same angle. So if I were to draw a normal to the surface at every point of incidence, you'll notice that those normals are not all in the same place because they are perpendicular to the surface. And so that means that all of these angles of incidence are different. And the law of reflection works for each individual ray. So if I draw an angle of reflection here that is equal to this angle of incidence, there's my reflected ray. Now I draw an angle of reflection that's equal to this angle of incidence. My reflected ray goes off in a different direction. So if I apply the law of reflection at all of these incident points, you'll notice that my reflected rays are scattered. This is called diffuse reflection. Okay, sorry, this is a leftover from our solar collector. Let's not worry about that. Okay, the point is that the smoother your surface, the more regular reflection you're going to get. So there is always reflection. The law of reflection is always obeyed. It's just not always that all of the light rays come out parallel to the way they went in. Right? We can also do this for any wave, not just light. So let's look at a somewhat circular wave that's propagating out, right? If we look at every single one of these rays, so we look at the middle one, right? It is hitting itself perpendicular to the surface. So that means when you draw the normal, that's a 0-degree angle. So that particular, in that spot, the wave just bounces back out. Whereas you'll see that on the outside rays, right, each of those rays is perpendicular to the wave fronts. It comes out at a different angle. So this is reflection, and this is how it works. Remember that we saw reflection on the wave generator for a transverse wave, right? So keep in mind that when we talk about reflection, right, in this case, it looks like an angle, but we're also talking about something that could be coming back at 180